Hello everyone, let's take a look at our next problem. So this one comes from a viewer submission through email. I'm going to read the email briefly here, and then there's a lot written. I'll summarize it and skip straight to the problem when it becomes clear what exactly is being asked. The positive rational numbers may be arranged in the form of a simple series as follows: 1 over 1, 2 over 1, 1 over 2, 3 over 1, 2 over 2, 1 over 3, 4 over 1, 3 over 2, 2 over 3, 1 over 4, and so on. In this series, every rational number is repeated indefinitely. Really, this should say every positive rational number. But anyway, thus 1 occurs as 1 over 1, 2 over 2, 3 over 3, and so on. We may list the positive rationals without repetition by removing those values from the list, which have already appeared in a simpler form, thus obtaining the following: 1 over 1, 2 over 1, 1 over 2, 3 over 1, okay, and so on. There is a function f p q such that p over q is the f p qth term in 1, where p and q are positive integers. Namely, fp of q is equal to 1 over 2 times p plus q minus 1 times p plus q minus 2 plus q. Find a function f of r such that r is equal to the frth term in 2, where r is a positive rational number. Ooh. Wow, what, So of course I've seen this kind of construction of the sequence of all positive rationals before. And I suppose the first function we're given, fpq, I probably could have figured out that expression from the construction. But fr seems difficult. I'm going to start sketching out, first of all, I'm going to sketch out the grid which corresponds to the construction of the first list so we can see exactly what is going on. Okay, so I've written out this grid up till p and q being equal to 8. And in terms of the direction things are going, like that, and then 3, 2 over 2, 1 over 3. Yeah, we're sweeping down this way to create the first list. We're going from, okay, I'm just going to keep that direction of lines in mind. We're going like that. But then how do we sort of count the ones that we remove? First of all, I'm going to put a little dot in all of the squares where we would skip over the number. So 1 over 1 obviously stays, 2 stays, a half stays, 3 stays, 2 over 2 we would skip, 1 over 3 stays, 4 stays, 3 over 2 stays, 2 over 3, 1 over 4, 5 stays. 4 over 2 is equal to 2, which we already have. So that gets skipped. I have an idea already that's coming out, but I'm going to continue. I'm going to continue first. 3 over 3 gets skipped. 2 over 4 gets skipped. 1 over 5 stays. 6 stays. 5 over 2 stays. 4 over 3. Yeah. 3 over 4. 2 over 5. 1 over 6. Good. 7. 6 over 2 skips. 5 over 3. 4 over 4 skip. 3 over 5. 2 over 6 skip. Okay. 7 over 2 stay. 6 skip. I'm going to continue a little bit here. The idea that I had was maybe looking at, it's almost like what is the thing where you cross numbers off that are non-prime and you're left with the primes. It's the sieve of Eris something, some Greek name. I don't remember what it's called. But it looks like almost something like that is going on here. But let me continue to see if I can kind of extract a pattern of some sort. So like I'm thinking the final answer here, f of r, is to write r in lowest terms, p over q. Then use the function we're given, f of pq, but subtract something about subtract something that has to do with prime factors lower than p and q or something like that. I'm not really sure. Okay, I'm not actually going to bother filling in the rest of these empty spaces. I'm just going to continue with putting my dots into the spaces where the number will be removed. Maybe a better way, an easier way to see this is rather than going down these diagonals, but going across a row. So 9 over 6 can be reduced. It's basically you put a dot in any square where the fraction can be reduced. So yeah, the way to you skip a square if the fraction can be reduced, because if it can be reduced, is that true? Hold on. Because yeah, the list is created by going down diagonals in this direction. If it cannot be reduced, then it has not appeared yet, right? It's not possible for a fraction to have appeared before if it can't be reduced. And if it is reduced, then the equivalent thing it reduces to has to be in that direction. So it has appeared before. So what we need if R is rational, let's write R as P over Q. Then and we'll assume in lowest terms. Okay, so P and Q are in lowest terms. As an example, let's say it's 7 over 4. So basically what I need to do then the place in the list of this of the original, the place of this number in the list, in list number 1, we have the function for that. We're going to take that as given. But its place in list number 2 is going to be equal to its place in list number 1 minus the number of blue dots that appear above that line. So how do we count? Well, the number of blue dots above that line, or on this earlier part of this diagonal. So for example, if I had chosen 7 over 5 instead, you know, we have a whole bunch of blue dots that we need to remove. Okay, so let's first start by figuring out, is there a formula for how many blue dots are above that line? So first, all the places above PQ these are of the form m divided by n, where m plus n is less than p plus q, right? Like on this line, the numerator plus the denominator is always equal to 11. And above this line, or to the top left of this line, the numerator plus denominator is always less than 11. So that gives us a description of, you know, all of the squares that we need to look at. So we would need something along the lines of pairs m and n such that m, n are not relatively prime. So that's how many dots there are to the top left of this diagonal. And then of course we would have to remove anything up there. So I'm going to write a description of this function f of r. So G P of Q is how many spaces in the grid have to be removed. I'm going to cheat here big time, and I'm just going to call it the cardinality of some set. So this handles all of the squares to the top left of the diagonal that we're kind of concerned with. But we also need where m plus n is equal to p plus q, with I guess m strictly greater than p. Actually, let me write it like this. Okay, so kind of a cheap cop-out way of doing this, but I don't see an elegant or simple way of doing this in terms of P and Q with, I mean, maybe there's some crazy thing in terms of, what is it called? Euler's 5 function, where you count how many, given an integer, count how many factors it has, something like that. But I don't want to go down that rabbit hole. So what have I done here? So I've basically defined the set of all ordered pairs where the square has to be removed. First, we have to look, this here defines the ordered pairs that are to the top left of the diagonal corresponding to PQ. And this corresponds to the ordered pairs that are on the same diagonal, but to the top right on that diagonal. And then we're only looking at the ones where M and N are not relatively prime. These will correspond to a square that has to be removed. We're going to take the cardinality of that set, and that's how many spaces basically this rational number gets bumped up that many spaces in the second list as compared to the first list. I don't really see, again, maybe there's a way of doing this more elegantly in terms of a function that counts prime factors, or a function that counts common factors between numbers, something like that. But I don't want to focus on this for a huge amount of time, and I'm not really an expert in that kind of math anyway. Yeah, I think this is kind of like the best I'm going to do. I'm moderately happy with how clean the solution was, or how clean the final answer is. But I'll leave it to you to try and find something more elegant. If I have anything else to say, I'll put it down in the description. Otherwise, thanks for watching.